Okay, let's start. So, firstly, there are a couple of items out here. One says Electrobot port control something. I think this is. Uh, I don't know. Do anyone of you recall? These are all the orders from the class, and the other one is Ikeshu four-wheel two-layer Arduino DY something. So that's yours. Yeah, I think it's a car-related one. Yes. Okay. If you had stuff on the list, make sure to ping me because sometimes the items carry names which you might not recognize. And I still have some more which are supposed to come tomorrow. Okay. The other thing is you saw my email about Amr, so he is still out. I believe he's still hospitalized. So what I'm going to be doing is I'm going to hold an extra office hour, and I'll do the discussion section myself. So let's deal with it, and I think if it doesn't get sorted out this week, then I'll figure out some additional arrangement for the closing part of the quarter. G has volunteered to help out, so just write to him if you have issues about the hardware software, and I've also requested him to monitor Piazza. So any questions on that front? The other thing is we now have 2 instances of people breaking the screen of the Hexaware. So a couple of comments. I mean, that connector is pretty fragile. And the other thing is do not remove that top part, okay, in the sense that bezel and kind of the covering on top of the OLED display. If you remove that, then this is a bare bone circuit and you're dealing with kind of the glass OLED display and that cracks. So keep that protective thing on. If you still run into trouble, so you can get it replaced, and B, you can borrow. I still have a couple of more lying around, so you can borrow from me. Okay, I think you have mine. Okay, if you can return that so that I'll have some spare ones for others, that would be great. Okay, so to recap from last time, and hopefully today my pen is working properly. So we were looking at sensing, and in particular, we looked at sampling, and I talked about. I mean, there is a usual Nyquist sampling, and it applies. So a few things that we covered. It is both time and space. The other thing is the reason it assumes something about the signal. So assumption that signal is band limited, and in particular we know F max, and the other thing is our goal is reconstruction. Namely, I want, after sampling, I have a set of samples, and given that sample, I can always ask the question, what was the value of the analog waveform at some point time t? Okay, so we can estimate, that is, given sample, we can get f of t, right? So that's our strategy. But as you can see, both these assumptions could be broken. I can know more about the signal, and the other thing is my goal may not be reconstruction. The other thing we saw was concepts of downsampling, upsampling. So upsampling is basically I want to increase the sampling rate, and that is I mean, one way of doing it is I can always go back to the analog signal and sample it at a higher rate, but you can just do it all in the digital domain. Downsampling is trickier because when you downsample, it may be that the new sampling frequency is not complies with 2 times Fmax, and therefore you may have to do some filtering also along with it. We also had anti-aliasing filters, which is, so these were other issues that we kind of looked at. So today what we are going to do is we are going to cover a topic which gain a lot, which at some level is simply about could we do better than Nyquist sampling, but a lot of the work in this space happened in the last, let's say, 15 years or so, and it has resulted in some pretty cool things. And the reason, so intuitively, think about it this way: if our sampling was so great, then how come we can compress the signal after we sample it, right? I mean, you digitize an acoustic waveform, and then one of the very first things we do is we compress it. So clearly, and we can compress it pretty well. That means that there was a lot of redundant information, and that holds true even for almost any type of sensing waveforms. You take your accelerometer data, and in fact, you can, if you feed it to GNU zip or zip or anything like that, and it compresses, right? I mean, so even a lossless compression, it does pretty well. So obviously, when we are sampling it pretty redundantly. So compressed sensing is this notion that could we sample and compress at the same time, in the sense that we just need to sample what is truly the new information. And at the end of the last lecture, I had kind of just thrown this remark that if you think about a sine wave, then Nyquist sampling says you will sample 2 times f max, but sine wave only has 3 parameters, amplitude, frequency, and phase. So I could sample just sufficiently to estimate those 3 parameters, and then I'm done. So clearly, if I know more about the waveform in that case, I could do better. So let's build upon that. So what we have out here is, let's imagine that I have some signal and I'm looking at it in the frequency domain. Okay, so in this case, what you see is it has spikes at 4 particular frequencies. So it's some sort of a mixture of 4 sine waves. Okay, and you can imagine these kind of things often occur. I mean, they're often artificially generated. Maybe you have a microphone which was listening to some synthetic sound and all, and then you might see these kind of things. Now, looking at this, as you can see, it's very sparse in the frequency domain, right? So that's the part which sticks out here, that it's not like the normal view of the spectrum that you see kind of some sort of an envelope, but you have this. And oftentimes what you might see is signals that may have a few dominant peaks and then a lot of crud around here, right? I mean, for example, let's say you are monitoring a human walking, okay, with an accelerometer in the hand. So there will be some very dominant frequency because we move our hands in somewhat periodic manner, and then there's a lot of noise and all that you will see. Or for example, if you monitor, let's say, voltage or current on our AC power supply, then again, there's supposed to be kind of clean 60 hertz signals in this country, but there's going to be a lot of noise and all, right? So there'll be some dominant things and a lot of junk. And usually those things are not, that noisy part and all is not of interest. Most of the energy is sitting in these dominant frequencies. So if you think about it this way, then much of what we seek out of a signal like this perhaps could be captured by those frequency elements which are carrying most of the energy, and we would get a reasonably good replica, hopefully, with that. So if I were to look at it purely from a Nyquist theorem perspective, then Nyquist theorem will say that I should sample at twice the bandwidth. And actually, the normal version of Nyquist theorem that we read about is sample at f max times 2. But actually, the way the math works is you have to sample at twice of f max minus f min. Okay, but that mathematical detail aside, I would be sampling at twice this frequency. But all we really care about are those interesting things where the energy in the signal is, and rest of the place we really don't kind of care about it. So could we somehow sample in a manner which relates to how much information the signal has? So what compressive sensing or CS allows us to do is to sample at a rate which is proportional somehow to the information content of the signal as opposed to just the bandwidth. Okay, so that's that's the goal, and um, how to go around doing it and systems doing this stuff and all kind of, like I said, came around in the past 15 years or so. By contrast, Nyquist sampling. Nyquist was active at Bell Labs in in 1920s, 1930s. So you're looking at like 100 years ago for the conventional thing. So what if I look at kind of the conventional view of the system, the way we do it is kind of the top one, which is we have some physical signal, we sample it, then we compress it. So in the digital domain, we compress it, and then we communicate, process, whatever goes on. Whereas the compressive sampling view is that we compress while sampling, so to say. That is, outcome of this compressive sampling box is a set of samples which are just hopefully the minimal that you need. And so it kind of just combines sampling and compression into one. Now, the challenge out here is that to be able to do anything with the signal, you will have to decode it. Okay, so and the decoding we'll see tends to be harder. It's actually computationally pretty intense, but it works out nicely because a lot of time our embedded systems and all are resource challenged, but you're sending the data to some cloud service or something which has more resources, so it can carry that additional burden. Okay, so so I don't even see the digital samples at twice the sampling rate. I just see a minimal set of samples coming out. So we are trading off complexity of receiver with the transmitter. So we have a more complicated receiver. That's what's going to happen out here. So if you think about what goes on in compression, right? I mean, we are basically when we take a sample waveform, then when we say that we are compressing it, what we are really doing is we are reducing the redundancy in that, so that we can express the signal in some sort of a minimalist form. So very broadly, there are two kinds of compression that we encounter. One is the lossless compression, which we use for data files and all. So you probably routinely use it when you zip it or GNU zip or any one of these systems, and there are sort of better versions like bzip and all. And there is an equivalent of perpetual motion in compression also, which has claims like we can compress any file by factor of 2 or something like that, right? Which is obviously impossible. So any lossless compression scheme will have to also fail at certain inputs, because I cannot, there is no such thing. But you'll see these kind of claims out there from floating around. But then we also have lossy compression. And the idea in lossy compression is that we make use of the fact that the entire signal is often not necessary. So like, for example, if you take acoustic signal, our ears are not sensitive to everything in the frequency, and moreover our ears are more sensitive to some parts of the frequency band and not other parts, right? We get less sensitive the higher the frequency. So you could play games like throw away less important information. So the signal that you get will no longer be able to be reconstructed perfectly, but the receiver cannot tell a difference. So lossy compression is good for natural signals, which is great for sensors, because sensors typically are for used to sample kind of natural signals. So lossy compression is not something you'll use for your C code and all, but it's great for most other stuff. So we encounter lossy compression on a daily basis when, for example, you communicate over cell phone. Wireless bandwidth is very limited, so the very first thing your cell phone does is it feeds it into a coder, which compresses things out. In fact, only the part of the frequency band which is which captures much of human speech, which is kind of like up to 8 or 10 kilohertz, is all that is sent out. And so if you send music over your cellular connection, it will sound lousy. On the other hand, of course, your phone needs to have a high quality microphone and all, because we also use it for local music playing and all. JPEG is another example where we compress the image. Anyone knows how JPEG works? not encounter. So uh, you should probably check out the Wikipedia page, because JPEG is a technology we encounter a lot, so it's good to know. But the way it kind of works is that it transforms the spatial signal into a spatial domain. So much like FFT, there is something called discrete cosine transform. So it transforms the image into discrete cosine transform, and then looks at those coefficients which are big, and it throws the rest away. And so along the lines of what I was saying for the spectrum, where we were retaining the dominant signals. Okay, in this case, it's this funky transform called DCT. So these are two classes of compression. So lossless one, like I said, we encounter a lot. This is anytime you're archiving files and stuff like that. And it basically, the way most of these schemes work is they look for patterns, and then commonly occurring patterns are encoded using few bits. So like, for example, if I knew that there was I had a finite vocabulary of words, let's say, and I knew that one word occurred half the time in the literature, then I can encode that using one bit, and then use the remaining additional bits to encode the less popular one. Anyone knows what that kind of coding is called, where you analyze the frequency? Huffman coding is what's referred to. So, but basic intuitions. So one of the ways a lot of these schemes work is that encode more popular sequences with fewer bits. And then you create some sort of a lookup table where you say, given this bit pattern, what was the original sequence? So, for example, the way GNU-zip, these sort of things work is they parse the file, they look for patterns, and then they assign bits to those patterns based upon the frequency of occurrence. There are other ways also. There's something called run length coding that you see out there. And the way run length coding works is, it says, oftentimes, if you look at bits, then I may have long runs of a bit. Like I may have bunch of zeros, like 100 zeros in a sequence. Then instead of transmitting those 100 zeros, I can say 0 100 times. So I can just send 0, n and make things extremely efficient. So that's lossless compression. But that's not what we are interested in out here. We'll be interested in lossy, but this just gives you an example that lossless compression is not particularly useful when we are looking at natural kind of things, particularly JPEG images. If you try to compress a JPEG image using zip, you're probably not going to see any win, or perhaps a teeny bit, just because there is some non-natural information sitting in those files. On the other hand, if you use, if on the images you were to use lossy compression, then you can kind of gain a lot of things. So let's see how lossy compression works. So the idea in lossy compression, like I said, is that this should have actually said lossy, I guess. Because that's what PNG is. So the idea in lossy compression, as I said, is you take into account that the receiver doesn't really care about full fidelity. If you were to look at the raw images in your camera, which are uncompressed, and you look at the JPEG images, for most people, they don't really matter if you have to be kind of some pro photographer and all to be able to do it. Likewise with compressed audio and all, that's how even high quality audio currently works. It's compressed, and when digital audio first came into being in 1980s and all, I was a grad student then, and I recall lots of people would claim they could hear difference between digitized audio and the vinyl record and all. And of course, after a while, all of that went by the wayside, because the quality is just so much better in so many other ways with digital. Okay, so how can we pull? How can we kind of go around doing this kind of a lossy compression at the time of sampling? So I mentioned that images, the way JPEG works is that we transform the image into a different domain. So FFT is an example of a transform which takes things into what we call as a frequency domain. But you could transform a whole bunch of different ways a particular signal. That's what we study in linear algebra. So given a vector, I can transform it, I can subject it to various transforms, and that takes up to a different basis. So that's a different domain. So what happens is that usually our natural signals we acquire in time domain or spatial domain, right? Time series or kind of some sort of a sampling of 2D or 3D space. So that's what natural signals look like. And they appear dense out there. I mean, if I look at a sine wave, it's dense in time, even though in some other regard, if I were to go to that parameter space of amplitude, frequency, and phase, it's actually pretty sparse. So if I were to be able to look at my sensor signal in a different domain, perhaps it is going to be sparse there, and therefore I can represent more compactly. Or likewise, this example I had a bit earlier out here, this one. So if you imagine, I mean, this is 4 sine waves of some amplitude and frequency. Well, in this case, amplitude is the same, 4 different frequencies and potentially some different phases. And if you imagine what the summation of them might look like, it might be pretty complicated visually and very dense in time. Even though looking at it in frequency domain, it's pretty sparse. So that's the concept that we bring to bear out here, which is by looking at the signal in some other domain. So we're going to transform the signal and it will be more compactly. So this is a sine wave example that sine wave really, as I mentioned last time, is just these 3 parameters: frequency, amplitude, and phase. So if you think about it, what this means is that if I were to take the Fourier transform of that time signal, then all it is saying is index of the FFT coefficient. Which coefficient? Because that tells us what would the FFT coefficients index tell us about the signal. Like I array the FFT coefficients. So if I look at the set of FFT coefficients, what do they represent? Anyone?
The weight of each frequency.
Frequency. They represent frequency, and the magnitude of the coefficient represents the weight. And the magnitude is complex number, right? And so that's where the phase gets captured. So amplitude and phase get captured in the complex value, and which coefficient we are talking about captures the frequency. So in this case, our sine wave would look something like that's shown out here. And by the way, this is just kind of an artifact. This is showing kind of that there is an imaginary value and then there's a real value. Okay, so there is a pair out there. So some sort of an imaginary number, or whatever, complex number rather. So I can represent sine wave very compactly. So lossy compressions, generally the way they work is that they try to see that what are the domains where we can take the signal to, and play this game of discarding those coefficients which are going to be less important. So in case of images, going to the discrete cosine transform is what is used, but you can imagine other ways of kind of doing it. A necessary property for this whole thing to work is that whatever transform I'm using should be invertible, because I'm going to play the game in this new domain and I'm going to head back. So I'll take my time signal, transform it into frequency domain, throw away some FFT coefficients, and then go back. So that act of going back and forth is also obviously important in terms of computational complexity, and it's called lossy because we are going to be deliberately throwing away information. There are a whole bunch of other ways that I don't know if you guys did it in your linear algebra, but like anyone heard of PCA's, principal component analysis? What does that do?
Yeah. You find a more compact matrix to represent more like of the original matrix.
Right. And how do we find the more, what thing that we do in PCA in particular to find the more compact?
Use the eigenvector and eigenvalue thing.
Yeah. So what we do there is we take the matrix, we do is eigen decomposition, which basically means we find eigenvalues, eigenvectors, and we take those eigenvectors for whom the eigenvalue was the highest. And that basically is representing where the most information was, and I throw away the rest. So this concept that I can decompose the signal into constituent parts in some basis, frequency, eigenvectors, cosine, discrete cosine transform, is something that you encounter a lot, and this is how we kind of compress compress things. We express a signal as a summation of its projections on different directions. And then in lossy compression, what we basically end up doing is that we discard those which are less valuable. Okay, so like for example, if you look at images, I could convey a lot of information to you by discarding the high frequency components, which would be the sharp edges, and you would still be able to make out. Or the other way around, I can give you the edge diagram, which is just retaining the high frequency components, and then you'll get a different type of information. So different frequencies have different information. So that's what lossy compression does. So in this example, what you have is, this is speech sampled at 8 kilosamples per second. So it's basically capturing up to 4 kilohertz. Okay, and then you could look at it in different ways. So in this case, what you have is the spectrum for this frequency, for this particular signal, and you could see that there are some peaks and a lot of low-level stuff. Okay, so what the game we'll play is, we are going to say we are going to discard coefficients which are small. So what we do is we retain only the top 100 coefficients, and that's this figure to the top right. And then we go back to the time domain, and I get the new signal. So again, what happened is we took Nyquist sample signal, we look at its FFT, we throw away all but the top 100 signals, top 100 coefficients, and then we go back in time, and if you look at this new signal, it kind of looks like the old signal. Okay, I think the scale out here is different because this one went to 0.2 and this one goes to 0.1. So, but actually, if you look at it, we are capturing, it's not identical, obviously, there are differences, but it seems to be capturing a lot of what we want, and you can play with how many coefficients that you are going to retain out of 4,000 coefficients that they have out here. So just a tiny fraction of coefficients. So in this particular case, the compression, so to say, instead of 4,000 frequencies, we are going down to a tiny fraction of that. So that's where we get our compressibility or our compression. So what we will transmit in this case, like your JPEG file, for example, is the coefficients in that discrete cosine transform domain. When you change the quality of JPEG, it's really changing the equivalent of how many top coefficients you are maintaining. And so the compressed representation is in this different domain. And then when your system displays the JPEG file, it does the inverse discrete cosine transform, just like we are doing the inverse Fourier transform to get the time out here. So that's lossy compression, and you can see kind of the gains you can have, and I'm sure you would agree that even that 100x, going down to 1% quality, where we are getting a 260x reduction in image size, still you can make out what it is. By the way, this image is one of the more famous images in computer vision history, which you'll encounter a lot. It's called the Lena image. And if you're interested in its provenance, which is kind of interesting, and just read the Wikipedia page. Okay, so compressing assignment. So assume we are interested in capturing a sine wave. So I knew somehow that the phenomenon that I'm sampling generates sine waves. I don't know its amplitude, frequency, phase, but I do know it's a sine wave. So an infinite duration sine wave can be captured using three frequencies. Three parameters. So really, the question that we ask when we say, can we reconstruct the signal? What we're really asking is, what's the best way to find the parameters? So the purpose of sampling is to gather information so that we can estimate the parameters. So any sensor signal fundamentally is about that there is some process, some natural process, some engineered process, something out there, and we are sampling it. And our goal is to estimate parameters of that process. Every process, like even if you look at, I don't know, like our electrical signals from our heart, they are generated by a physical process, some physical model, the beating heart, which has to do with the underlying electrical system and all. And it operates according to some physical equations, and those physical equations have some parameters. So what we really, at the end of the day, want to do is we want to know what are the parameters of that physical process, that physical system, which is generating the signal that we are observing. In this case, the underlying physical process is generating a sine wave, and it has three parameters, amplitude, frequency, and phi, and we want to estimate those. So what's the best way of estimating that? That's really kind of the question. So one thing we could do is the following. We sample above the Nyquist rate, at Nyquist or higher. We take, so now we get x of n, so we get a set of samples. We take the FFT of those samples, so now I get FFT in the FFT of the signal, and now from the FFT I can calculate the parameters, frequency, amplitude, and phi, and then we are done. So we could do that. So the rate at which we have to sample is anything above Nyquist, because we have to be able to reconstruct the signal. And how many samples do I need? Well, it depends upon how accurately you want to measure f. So for example, if I want to measure f coarsely, let's say only up to 1/100th of the bandwidth, then I will need 100 samples if I want to do it very. So it's the resolution with which we want to estimate f will dictate how many samples I need when I'm taking the FFT. So when you take FFT, you say n point FFT. So the n of the FFT will be what frequency resolution do I need. So in this case, taking Nyquist rate, so I have sufficient samples to reconstruct the signal. Then I do an FFT with a fine enough resolution, and then I can look at, hopefully I will just see one peak, or maybe I'll, because of resolution problems, I might see, well, I should just see one peak. And then I can measure amplitude and phi of that peak, and I'll be done. But this is what we want to avoid, because to capture the sine wave, to learn about the sine wave, I'm having to capture so many samples. So we want to do better than this. So method 2, what we can do is, I can take my analog signal and I can feed it into a set of analog filters, each filter tuned to a tiny part of the frequency. So let's imagine that I have some number of filters out here, and they each only are sensitive to a tiny part of the spectrum. So what will happen is, output of one of those filters is going to be active, and the rest are not going to see anything because they're tuning to very sharp things.
How do we choose the filter banks?
How do we choose the filter banks? Because I will assume that just like in the Nyquist case, I knew what is the F max. That's it. Okay, so I can just cover that 0 to F max, and based upon my resolution, I can have a set of filters. And then I can threshold their output to find which filter was the one which was active. So that gives me the F. I can look at the value of that output to get the A. And then finally, to get the phi, I can play some other circuit games where basically what I do is I try to learn let's ignore this part, but basically using some phase block loop circuits, I can estimate the phi. So I can go down that route also. And in this particular case, again, the number of filters I have will tell me, will control what frequency resolution I can get. And so this process can work too. But again, very hardware intensive, lots of analog hardware needed. So compressed sensing goes with the following intuition. It basically says that, look, my signal I know has only 3 parameters. So really what I need is 3 good measurements, 3 equations, and then I can solve some mathematical problem as a result of those to get my 3 parameters. And so that really what boils down to is what should I measure, and how, and from that how can you get F, A, and phi. And I'm presenting it in context of just a sine wave, but you can imagine a more general system may have some 100 parameters. So hopefully I only need to take order of 100 measurements, and then I can be done with it. So let's say, to start with, let's say we knew the frequency of the sine wave. So I simplified the problem even more. I know that the source is generating sine wave of a certain frequency, and all I care about is the amplitude and the phase. This actually is a fairly realistic problem. You might face it in, let's say, if you're designing something to monitor power of the AC power of some appliance. The frequency is known to be 60 hertz, and it's really the amplitude and the phase which can tell you about the appliance. So can we just use 2 measurements for this? So let's say I was looking at some time window and I took 2 measurements. Okay, so one shown in red out here and one shown in red out there. So now what we could do is, I know I have 2 measurements. They correspond to some time at which I took. So I took those measurements at time t1 and time t2. And since I know that the sine wave, the underlying thing is a sine wave with a particular frequency, but at unknown amplitude and phase, therefore I must have 2 equations like this. That is A and phi, which we don't know, F, which we do know. So I must have my first measurement be A times sine 2 pi ft1 plus phi, and my second measurement Z2 would be A times sine 2 pi ft2 plus phi, right? Because I know about the underlying thing. So I know Z1, Z2, T1, T2, I know F, and I have to solve for A and phi. Do you think we can solve it? Yeah, right? I mean, it's kind of would be some messy equation manipulation, but you certainly could do it. So now we can just extend this concept to multiple sine waves, multiple unknown frequencies, but the basic concept is the same, that I know a parametric model of the underlying process. I'm sampling it, and so that's giving me a set of equations, and now I have to solve it. And generally speaking, it's going to be a highly nonlinear problem, so you make use of numerical techniques, but you could imagine that I could make a guess and do gradient descent, the various kind of optimization techniques that you could go for. Now the challenge also comes as what kind of solution we are looking for, and what if we have multiple solutions. But generally speaking, when we are faced with these kind of problems, we try to find a solution which minimizes some error criterion, right? I mean, so we often do least mean square, these kind of error criterion. So our goal is to find some assignment of values for the for the unknowns, in this case A and phi, which minimize some error. And our error in this case, maybe I could define the error in terms of that using those A and phi, the predicted Z1 and Z2 will be close to the actually measured Z1 and Z2. So I can define, I can approach this problem in this manner. So what we have suddenly done is we have taken our original sampling problem, which was in terms of Nyquist thing and all, to now a parameter estimation problem, and then we use optimization methods to find a good solution. So And generally speaking, it would be some nonlinear model. So we'll be using, and I mean, we have tools like MATLAB and all to kind of do that. So I could do it this way. The other ways of doing it also, what I could also do is template matching. So I knew the frequency, and then what I can do is I can take a template of that frequency, and then I can alter its phase and amplitude. So kind of do a search in the space. So I can take a template and mess with its A and phi, and eventually we will have some match. Okay, so I can, in this case, I'm again trying to find a template A and phi such that the template will result in a good match. So I could do that also, and so I'll vary the phase and amplitude of the template, and then keep making a correlation between the two until I hit a peak in the correlation, and that will tell me I have found my A and phi. So you could imagine various ways. It's fundamentally a search problem. We have A and phi, which are unknown, and so I'm going to look for what values of A and phi result in the signal that we saw, result in the measurements we made, right? So fundamentally the problem is what values of A and phi will result in my equation leading to something which is close to or identical to Z1 and Z2. So those are a couple of ways you could do. What compress sensing does is the following, that it basically does what I've been kind of implying, that think of a space of parameter, in this case it's a two-dimensional space, A and phi, and my goal is to find that point in this parameter space, that combination of A and phi, which minimizes which optimizes some cost function, some error, okay? So, and what it does is, each time I make a measurement, I'm basically constraining where I have to search in this space. So every time you have a measurement, some part of the space is locked off, and then eventually there is an area, there's a volume in this hyperspace that is left, within which you will have to search to find a value of A and phi, which are good. So so by applying mathematical tricks, they kind of seek to reduce the search space. So instead of doing exhaustive search over all values of A and phi, you actually are going to search only over a much tinier volume. So that is how one can get the efficiencies.
The windows set by the constraint width,
or? The windows result from the constraint. So I'm kind of doing a bit of a hand wavy argument out here, because A and phi, if you allow anything, then it's the entire real number space, right? But every time I'm making a measurement, I'm placing some constraint on what set of values they could be, and kind of that results in smaller and smaller amount of things. So for example, I mean, if it was a linear system, every time I tell you something, you kind of begin to rule out part of the feasible space, okay? And then when you take the intersection of all the constraints you have, you're kind of left with a smaller search space. So so it's the same sort of game that ends up getting played out here, except in a more complicated mathematical setting.
because A has no limit, so but phi has certain limit. So
Phi has certain limits. So phi obviously is a bounded thing. A has no limit as it starts out, but you can begin every time you are taking a measurement, it is telling you something in a stochastic manner, at least where things would lie. So that's what you're going to make use of. But what's going on is, I mean, to be able to solve these kind of problems, if you look at MATLAB's optimization toolkit or any one of these numerical packages, they offer these things. They basically take a set of nonlinear equations, and they give you the best estimate according to some error criterion. In this case, our error criterion simply could be that the estimated Z1, Z2 should be very close to the actual measured Z1 and Z2. And so I'm looking for, formally my problem becomes find that value of A and phi so that when I predict what the equation, I use the equation to predict what Z1 and Z2 would be, namely the values at time t1, t2, they will be very, very close to my measured values. So, and that's what these optimization algorithms kind of do for us. But we'll seek to place some additional constraint on it, as we'll see how sort of it works out. So what you see out here is an original signal, and then the signal constructed using just 3 samples. So this is a sine wave. Remember, I'm trying to now reconstruct the sine wave. So I only took 3 samples. Not Nyquist would have given us a whole bunch of samples in this case, right? We only took 3 samples, and this is the reconstructed signal, the middle left one. And you can see it's pretty lousy. And therefore, when I look at the error between the reconstructed signal and the original signal, it's pretty bad. It's basically kind of the original signal pretty much in this case. But on the top, on the right hand side, what we are doing is we are taking 11 samples. So instead of 3, we are doing 11. Still a very low number, right? I mean, if you look at this particular thing, it's actually the number of samples. If I were to sample at twice the frequency here, I mean, I don't know how many peaks, how many cycles we have, but look like 50 or so. So you'll probably need like 100 or some odd samples out here to pull it off. Just with 11 samples, I'm getting a reconstructed signal which looks like middle right, and the error is pretty much close to 0. So what this shows is that so while we didn't quite achieve our goal of 3, because in this whole story we also you have issues of numerical stability and how well our optimization algorithm is doing, but we are pretty good. I mean, we reduced the number of samples tremendously relative to what Nyquist sampling would have yielded. So while 3 did not work, 3 is what theoretically sufficient, but we could also be unlucky if you pick 3. Maybe all 3 are at the peak, so they're not giving us sufficient information. But 11 in this case, which are, yes, we haven't shown it, but yeah, sorry, we've shown out here 11 sort of suitably, they seem to be arbitrarily dispersed, give us a pretty good thing. It turns out that you don't have to select those 11 samples particularly smartly, just randomly. So the strategy of random sampling and sufficient number of random samples and then doing this estimation game works beautifully. So now in this case, what's happening is instead of operating our A to T converter regularly on a Nyquist sampling rate, we operate the A to D converter at some random times, but in that time window, and then we apply essentially this approach of find. So basically, I will write it out here. Find A hat and phi hat, which is estimates, namely estimates, such that Z1 hat and Z2 hat, that is predicted from A hat and phi hat, are close to Z1 and Z2, which were measured. And this strategy, generally speaking, you can imagine, can always work. Now, what I have not talked about is what are those algorithms which will kind of do that optimization beyond the purpose of this course, but they exist as tools for it, tools for you in MATLAB and other libraries. So we can certainly do it. And this is basically nonlinear optimization. Okay, so what's happening now is this time series that we had, originally we were sampling the time series at the Nyquist rate, right? So there was a regular sampling, and the output of that sampling would have been a vector. Except now we are saying, let's select 11 out of them. And we select those 11 out of that vector of whatever length it was, we're selecting it kind of randomly, okay? And why 11? Because our experiment showed that 11 gives us good reconstruction ability. 3 was too few. So you'll play. So the idea is you'll play with some captured signal to find out what kind of sampling rates are going to work and work with those. So now what's happening is this process of selecting that 11, that can be looked as essentially selecting from a vector 11 random samples, or another way of saying is that I'm taking my original signal x and I'm multiplying it by a matrix phi where most entries are 0, some entries are 1. And so therefore I get a z, which basically is selecting some of the samples out of x. In our case, it would have 11 ones and rest of them 0, so it will help me select. And this is a random matrix. So, so after I have sampled, in this case, the phi would select kind of 3 samples out of x. So, so you can view this act of random sampling as a random projection. So phi is projection. So I'm basically taking my original signal and then I'm going to subject it to basically what's a linear transform, but which is actually in the form of a random matrix. And now what we will do is one thing that we do know is that I expect my signal to be sparse in the FFT domain in this particular case, but sparse in some domain. So what we do is we go into that domain, and when we say something is sparse, that is another way of saying most coefficients are 0. So I want to find a solution so that my reconstructed signal, when I were to put it into a frequency domain, will have a small number of non-zero coefficient, or in our case, just one coefficient. So in this particular case, if we are doing our job right, then our values of A and phi should be such that when I take the signal into FFT domain, I should just see one peak. More generally, what this thing says is that let's select a transform, in this case it was FFT, where my signal was sparse. So that domain may be FFT, but it could be something else. And the constraint is now becomes that I want to find a solution which results in few coefficients in that domain. And few basically means that I want to find a solution which is what is called as the L0 norm in optimization. So it's a distance metric. So if I think of a vector and I'm trying to look at the distance between the length of a vector, then L2 norm is our classical distance, Euclidean distance. L1 norm says I want to minimize the absolute value of the coefficients in a vector. L0 says I want to minimize the number of non-zero entries. This is something, again, you would encounter perhaps in other courses, but intuitively what we are going to aim for out here is we are going to look for those solutions which result in a sparse signal, because we started out with a sparse signal. In case of sine wave, it was very sparse in FFT, but almost every signal that you look at is sparse in some domain. And the reason they are sparse in some domain is because natural signals are not generated randomly. If they were random in every domain, that means they're noise. They don't have any structure. So since natural signals are generated by some sort of mechanism, whether it's a beating heart or a functional brain or a car driving by, they're all generated by some process which has a small number of dimensions. and therefore there would be some domain in which they are going to be sparse. And if we know that domain, we can make use of that knowledge. And in this case, we know that it is sparse in frequency domain. So I can look for a solution that was sparse after FFT. So FFT would be my preferred domain. The problem that happens is that if you look at some natural signal, you have no idea what domain it is going to be sparse in. You can have some intuition in some cases like these, but and if you do, great. But what if you don't? What if it is, let's say, I don't know, signal from the hexaware as you're moving around. So it's certainly being generated by the way we move and all, and therefore it has some structure to it. Our hands don't move in a white noise fashion. They're controlled by our body mechanics. So there is some structure to that, but we have no idea what it is. So I'm going to skip this part, but the key result, this is just kind of, you can skip these slides. It's basically just saying that how to go around solving that underlying problem. And I was referring to L0 optimization. I'm looking for solutions which are simple, solutions which have few parameters. But the main result which came out around 2000 time frame by Professor Terence Tao out here, heard of him? How many of you have heard of Terry Tao? Everyone. Why is he famous?
Cryptography or
No, not crypto.
the prime number.
Well, he got the Fields Medal, right? But he has done a broad body of work in that. But one of the things that he did was the theory behind compressive sampling, together with this person, Candice, who used to be at Caltech at the time and is currently at Stanford. So these guys were ignoring some prior work apparently in Russia long ago, sort of in the 90s and early 2000s. There was a lot of work which emerged. And what these guys showed was that for almost all random projections, that matrix I had, and then doing this kind of optimization works beautifully. That is, you can subsample and reconstruct in this manner, and kind of essentially reasonably arbitrarily selected random sampling approaches work fine for most natural signals. And what it is basically saying is that natural signals have a natural sparsity which gets exploited out there. So the theories behind this and all are way too advanced for a course like this, but the thing I want to leave you away with is the following, that at the end of the day, what's happening out here is that instead of sampling in a Nyquist manner, we are going to basically sample subject to some random selection out there at some random points. It could be in time, it could be in space, and then I'm going to convert my reconstruction problem into an optimization problem, and then now look for signals which are sparse in that domain, that is, which have few coefficients in it. And it turns out that the scheme works very nicely. Okay, that so in recent, again, 10-12 years, there have been all sort of cool stuff around it. Like, for example, Rice University, which is another place where a lot of work in this discipline has happened, they have created things like they call a single pixel camera. So instead of cameras where, our normal cameras have whatever nowadays a few thousand by few thousand 4K pixels and all, right? Huge number of pixels. And so you capture a lot of data and then we compress it. So what those guys do is they basically, so stepping back, that works great for optical cameras, but in many type of other cameras, the pixels are very expensive because they may be for X-rays or some other part of the spectrum. So now what happens is you take a single pixel and you're going to make measurements in different directions. But you cannot make 4000 4K, right? 4K is what? 4K is a few million pixels, right? You cannot make that many measurements. It will take eternity. So what they do is they take measurements in a few random directions and then play the same reconstruction game. Okay, this is called a single pixel camera or whatever, few pixel camera. Generally speaking, these kind of concepts have been used for all sort of things. What it saves is power, because what's now happening is you're capturing very few samples and then you're just going to send it out. So imagine a wireless sensor which is capturing the sample, sending it out, and the reconstruction is complicated. I mean, I couldn't even explain the map to you because it's beyond, because it requires all this optimization and all, but the thing is, it's being done in the cloud. So the embedded side is super simple. The only thing is you're no longer, you could approach it one of two ways. One is you make your A to D converter sample at random points, or the other is you sample the A to D converter with Nyquist rate and then throw away, randomly select a subset and then ship it out. If you're interested in kind of a more accessible intro to further details on how compressive sampling works, this URL actually has a pretty good general seminar talk around it. So that's compressive sampling, and what it has shown is that for natural signals, it is not necessary to sample at Nyquist rate in order to get good quality. That is, you can get pretty good quality with factors less sampling rate. Some years ago in my own group, we were kind of also working in this area, and we tried it for things like physiological signal, like ECG. If you look at ECG signals, I'm pretty sure sometime in your life you must have looked at some waveform, right? They're insane. Not much happens in the middle, and then there is cluster of peaks, and again nothing happens in the middle. They're sparse in time, right? There's not much happening there. And actually that also sparse in frequency. Okay, so people have applied it to those. People have applied it for all sort of other physiological signals, accelerometers, things like that. So you could certainly sample less than Nyquist rate and still get away with obviously not perfect reconstruction, but pretty good high quality reconstruction as a result. Other work in this space has also said, I can even do computation over over compressively sampled things. So what that says is, let's say I want to find which frequency has the highest amplitude, or maybe some other question about the waveform. So normally you would say, okay, I can only answer it by reconstructing the waveform. Like maybe I want to know how often was the signal crossing zero, okay, those kind of questions. It turns out many of this computation you can do while the signal is still in that compressed domain, okay, and still answer those questions. So there's a lot of theory and all which have developed, again, kind of way beyond, I mean, those are topics in advanced graduate courses, so beyond our scope. But there is sufficient software floating around now that for practitioners to use this kind of stuff is certainly possible. Now, another way you can be smart about sampling, and I just gave the example of ECG signal. So ECG signal looks like this word, right? Right? So some stuff like that, okay? And doctors have all sort of names for all these different kind of peaks, P, Q, R, S, all sort of medical jargon around it. But at the end of the day, the thing is, there isn't much happening out here of interest. And the other thing is, this is reasonably periodic. So how would you go around sampling if you knew that it's an ECG signal and you want to be smart about sampling it? And you don't know compressive sampling. So what would be some alternative strategy that you will apply? Title should give some hint. Adaptive sampling. Could you think of an approach where you are not going to sample it continuously but skip samples?
Maybe you could get a sample that isn't on that line then you start sampling more rapidly for a while, and once you get back to flatline stuff.
Exactly. Right? So I'll sample densely for a short bit. And I know it's an ECG signal, so I'll sample maybe the first few cycles I will sample densely, get a sense of what this period is, allow for some margin because heart rate is not perfectly periodic. In fact, it varies with stress and things like that. And then what I can begin to do is, my goal is to sample densely where action is happening and sample very, very sparsely where not much is happening. So I want sparsity out here. And here I want dense sampling. Intuitively, I should sample more where things are changing more, right? Or I think in a previous, in the discussion section on Friday, I talked about like sampling. Imagine a robot is sampling the light intensity on the floor of this room. So there are regions where the light intensity is just flat, so it could make a sample race ahead. And whereas if it's under the chairs where there is a lot more light and shade dynamics, it can sample more frequently.
Also, we do threshold-based sampling.
Yeah, so threshold meaning that how much the signal changed. Okay, not threshold in terms of absolute value, but so what this is saying is, so the robot, what it can do is it can take a step and say, aha, did the signal change a lot? And if so, it can go back and collect additional samples. With time, I cannot do that because I cannot go back in time unless you have some sort of funky analog memory. But what I can do is, in this case, I can kind of take an estimate, say, the heart is beating at whatever, 60 beats per minute, roughly. I'll budget for some margin because the person may be running or something like that, and then do it. It's a little bit like our wake-up problem, right? When do I wake up the sensor, okay, without knowing the future perfectly. So that's what's happening in case of time. Okay. So adaptive sampling is an alternative sort of way of being smart about sampling. So let's look at it in context of a control problem. Actually, I just noticed that we are a bit past 5, so let's do a short break and continue. So 5 minutes.
Yeah. I guess the first question is is there going to be one? Just one? Yeah.
Okay. So with the deadline, would that be the same with the project as well?
I just want to make sure that everyone has done the
Okay. Okay, and then as for the project, when will we be hearing back from our proposal? Or will
no, the proposal was just so that I can they're all okay.
Oh, okay.
Yeah, so you just move ahead with it.
Okay, if we want to change anything about the project,
You're fine to change. It was for me to force you to have a proposal
Oh.
and also any parts that you need.
oh, okay,
That's it.
okay, thanks.
And I guess like how intensely in depth built out would the project have to be? How complex would it have to be? Like how complex would the project have to be? Do well, I guess.
Like is complexity part of the rubric?
Yeah.
I mean, I guess the main thing is complexity as a function of the team size. I mean, like obviously I expect more from a 3% team than a 2% team.
Oh,
Okay.
sure. But if you've already reviewed all the proposals and it's all good, then I guess it's
Just remember, it's going to be reviewed by your peer group. So
Okay.
that's it. Remember, right? I mean, we're having
it's a peer. Okay. Alright.
Okay.
Thanks. Yeah, so I can fill out the form. Basically, for you, run for you. I'll go and reveal my project.
So I usually do
Yeah. Yeah, just take it around. It's like, and the Raspberry Pi. So they have my data cards, but I just check out. A lot of people tend to do this. Definitely on project.
I have to head out for another project, but then I was also wondering for the project itself, what if we integrate like Amazon cloud infrastructure?
I want to use the project to explore other
Because I
technologies.
was looking at IoT core on the
So, I mean, there's obviously the whole Amazon IoT thing, and then Azure has a similar thing also. And we are using Raspberry Pi Zero, but if you have access to Raspberry Pi 3, then Amazon's IoT stuff can also run on the Raspberry Pi. So they have this model, something called Lambda functions, which are okay, and I think it's called green grass. Right? Yeah. So more explore.
Yeah, they also
So,
have like
so I think those are the things that I would reward, like in the sense, did step out of your
yeah,
comfort
because
zone
I'm like
with
looking at it, it's like all really new, but it's also like pretty cool. So, yeah, I'm like,
Go for it, absolutely. Yeah. Some couple of the groups are also doing it.
okay, also in terms of like cost, how would that factor in? Because I know that like Amazon infrastructure, like it does cost to use.
Since I'm assuming you're using the AWS Educate, or
Yeah, so I have like credits for it. I'm just wondering like, how will that
I will-
calculate its cost or
I will not comment.
Thank you.
Okay, let's start. So actually, something came up from a question out here. If you're using any cloud service like AWS and all, I will not count its cost towards the $25 because I'm assuming you have access to AWS Educate, which is Amazon gives you credit. I think $75 or $100. Those are beyond the project. So, okay, so. This thread is going to look at an alternative way of being smart about sampling, which is this notion that let's not do stuff that's not sample if there is nothing interesting happening in space or time. So this is going to be something where after looking at the signal, I'm making my mind. The nice thing about compressive sampling was that it's still a general scheme in the sense that once I have my random matrix fixed and all, it's like Nyquist sampling, except that it is just throwing away a lot of samples. Here we are going to examine the signal at runtime and then make a decision. And the particular context in which I have picked it up, mostly because this is work in Professor Padota Waller's group out here, you see, and kind of comes from control backgrounds. I'm picking control, but you can imagine doing it in other contexts also. So what happens today? Let's say we want to control the speed of a motor or position of a motor, and I encounter it in controls of drones and robots and all these kind of things. So you would have some sort of a command coming in this case, says position in degrees. And then I have a controller which applies voltage to the motor, and then we have a sensor position encoder. Way back early in the course when I talked about how pulse width modulated signals get used with optical discs and all, this is an example of that. And it feeds into the motor controller. It looks at the error between what the current position is and what the desired position is and applies some voltage. Okay, so that's what goes on. um, what the theory assumes is that I'm getting a signal from the sensor, the position encoder, on a continuous basis. So it has been periodically sampled, perhaps, but I'm essentially getting that continuous signal. So we put an A to D converter and then select some sample rate, and there is some whatever rules that some theory that control theory people have, which basically lets you decide how fast you are going to sample. Okay, and it's a lot of black magic actually also there. But main thing is that every time the A to D converter samples, then that sample is processed by the control algorithm, and it generates a new command for the motor, a new voltage, and then again we sample, and that whole process goes on and on. So it's a very periodic process, okay, and usually the frequencies there are going to be the frequencies there are going to be dictated by the dynamics of the motor, like the underlying mechanical the equations, differential equations that govern the motor. And fundamentally, the same thing goes on in almost any control system. That is, you sample the something about the system, the state of the system, and then based upon that, you make a decision, and you keep doing it periodically. In fact, this thing is used in factories, in your cars, and I mean, this basic loop is always there. But what if instead of sampling periodically, when we were to only sample when the position of the motor has changed significantly? So so actually, it turns out that the periodic sampling, which is kind of you are seeing on the left hand side, what's happening is we are sampling every quarter second, and what's happening clearly is that if you look about it, that if I were to look at the underlying analog signal, then the signal is changing a lot on the left side of the waveform because the slope is more, and on the right hand side it is decreasing, its slope is less magnitude wise, and therefore my each sample is corresponding to a tinier change in the signal. So what if instead of that we were to go with what is called as Lebesgue sampling, but basically the idea is that what if we were to sample when that signal has changed sufficiently? Only then we sample. So do you see a problem in this approach? I want to sample when the signal has changed sufficiently.
And the step size has to be adaptive.
It changes super slowly. You end up making a big change after.
I'm looking for a much more trivial issue out here, actually.
How can we sample, or how can we know it's changed?
Exactly, right? I mean, I'm saying that how do I know that the signal has changed sufficiently if I haven't sampled it, right? So that's a bit of it's a chicken and egg problem, right? So I have to find some way around it, obviously, to kind of deal with this issue. But if we could pull it off, then I'm sure you would agree that this strategy is great, right? Now, there's one way I can approach this thing. So back to this problem, how can I make sure that how can I do this sampling? So this one issue, and the other one is what should be that interval? Okay, that's the other question, right? Which is when should I sample? Let's say I've decided I'm going to sample this way. What is that gap? How much of a change is sufficient change for me to decide taking a new sample, right? So how do we decide that? So that second question obviously comes from the theory. So back to this question, that how could we make a system like this? So this is now into event-triggered sampling or event-triggered control, and kind of the basic idea is that somehow I'm going to monitor the analog signal using some module, some circuit, and the circuit is monitoring the analog signal, and it also has access to the previous sample we had, the previous measurement we had made. And then based upon those two things, it is going to decide when to trigger the A to D converter. right? So it is, it has the previous sample, which was taken at some time tk, and it has the current analog value. Obviously, this thing has to be analog, because if it was digital, then it would have defeated the purpose. So I would have some simple analog circuit, which will take this and this, and then kind of do it. So you could trivially imagine that maybe if I have a fixed delta, that is, I would say that I should sample when the new value, when I have drifted at least delta away from the old value, then it would be some sort of a comparator plus some other circuit. So you can imagine making this kind of a circuit. So that's one approach. That I create this analog circuit, which is monitoring, and at the analog level, it makes a decision and then triggers the A to D converter. So no more is the A to D converter being controlled by software, but it's actually being controlled by this analog circuitry. The other way I can approach this thing is I can go ahead and sample periodically, but then throw away samples based upon this policy. Okay, so I can skip over samples and then discard that. So that would be great if my bottleneck was the processing. If my bottleneck was actually collecting the sample, then it doesn't help there because I have to collect the sample there. And you can encounter both these kind of systems. There are systems in which cost of collecting the sample is high. And then there are systems where the collection of the sample is cheap, but processing is the one which dominates. So can you think of examples where cost of collecting a sensor sample is high? So what kind of sensors have costly, their cost is just capturing the sample, the capturing the value itself is going to be expensive. Yeah.
Like an MRI signal could be.
Okay, terrific. MRI signal, absolutely. And so in that case, because it's just so bothersome and all, right? I mean, but generally speaking, anytime collection of sample requires a lot of energy, like let's say radar or even camera, if I have to image in the dark, I have to do a flash, where it presents security risks, like maybe it's the army operating and every time you have to take a sample, you're exposing yourself and therefore the enemy can detect your presence. It could be costly because maybe the sensor degrades every time you take a sample. If it's physiological thing like, I don't know, blood finger prick and all, you want to minimize that. So you can imagine that sensing where energy cost or bother to the subject or security risks and all those kind of things, you would probably you would be dominated by the sensing cost and you want to minimize that. And then there are other settings where it's the cost of communicating it to the controller or the controller processing it is high. And that has begun to happen because now often sensors are wireless. So you want to, so while A to D conversion itself may be pretty cheap, let's say it's a temperature sensor, right? But why keep sending that data? Because the wireless cost dominates. I talked about previously that how wireless communication is pretty expensive relative to just that local processing. So it would be worthwhile for you to say, hey, yeah, did the value change much? If not, let's not send it. So where the sampling itself is costly, I would perhaps need to do some games like this to be able to pull it off. So the theoretical work by Professor Warner's group, what those guys did was they basically found what this rule is, that how much should the signal have changed for us to make it worthwhile sampling it. In particular, their rule takes the form that if the current signal is larger than certain fraction of the change since the last measurement is more than certain fraction of the current value of the signal, then I should sample it. So they kind of give a value of sigma and they show that they can find the sigma so that the overall control system works as desired. Okay, so it's called event-triggered sampling, and in the analog circuit, you have to implement this particular equation that is shown out here. Okay, that has to be implemented in analog. But more broadly, this is just an example of the sampling strategy where you are sampling, so only when, or you are either you are sampling only when, or you are processing the sampling only when there has been a sufficient change. And you get to define what is sufficient based upon your particular application needs. So, so generally speaking, what is happening is that you have a current measurement and you have some sort of a model of the system, and you kind of take all of this and then you say, when should I sample next? So this was my example of the robot. Let's say it's making the light field measurement on the ground, and it can kind of take a step, decide was a step too short, next time it will take a longer step. If the step was too long, next time it will take a shorter step. Or maybe it can even go back in time, right? I mean, so all those kind of adaptation strategies that you can imagine. Back to, let's say you were using Hexaware for some sort of human activity detection or something. If you are not seeing any movement, if the person is just sitting on the chair, you can save some energy, sample less. Right, so you could play those kind of games where, based upon your current estimate of what is going on, you control how the sensor is being used. Perhaps you don't even activate all the sensors. Right, so you think of sampling as a precious resource which you are going to use only when you believe it will give you something useful and something new. Okay, so I want to skip this part. Okay, so to summarize sampling then, embedded systems, generally speaking, they have to interact with the physical world, and they do so via the sensors. And before we can do anything, make any prediction, anything, we have to just be a fundamental question: when should I make the measurement? And what we did thus far was we looked at basically three broad approaches, right? There is Nyquist sampling, then we moved to compressive sampling, which basically said, Nyquist is wasteful because after we sample, we can easily compress. So why not do compression as part of sampling? And then finally, we saw this whole adaptive sampling, which is basically saying, if things are not changing, don't sample. Okay, so now let's move to the next bit, making inferences from the sensor data. So now we have the samples collected through one of those sampling schemes. Now we want to draw some conclusions from it. So a little bit about what role, how do we go around processing it? What kind of processing you do after you have collected the sample? So let's spend a little bit of time on that. And to do that, firstly, let's think about what role sensors play in these systems. So if you think about a system, and I'm using kind of a robot out here, so there are systems tend to have broadly two types of sensors, two categories of sensors. Sensors which help sense system's own state, and they are called as proprioceptive sensors, one's own. So idea is that a system should be able to measure about itself. Could you give me an example of a proprioceptive sensor in case of Hexaware? Accelerometer, battery, right? Those kind of things, right? So it's basically saying something about, well, so accelerometer is kind of a is an example which is perhaps could be considered in the next category, but battery is clearly an internal state. Internal temperature would be clearly in, okay? Exteroceptive sensors are the sensors which are measuring something about the external world. And so in case of a robot, it might be distance to nearby objects and all. And by the way, proprioceptive might be, let's say, wheel position, right? So in case of Hexaware, the reason I said accelerometer could be viewed as an example is because it's saying something about the body on which it is put. So it's measuring the acceleration of the body and not also. So depends upon how you kind of view it. Light level is certainly an example of something which is clearly external. So that's exteroceptive sensors, and almost all systems kind of would have both categories. So in addition to making inferences, which what I'm leading up to, you also have to do processing to deal with kind of the fact that sensor data is not perfect. It has noise, it has issues of what are called as conditioning, it may not be calibrated properly, so all of these things come into play. So let's look as an example a light sensor. Hexaware has one, our smartphones have one. They basically measure incident light intensity, so light falling on the system. Okay, so it's basically it's slightly different than kind of the diffuse light that we see, but to the first order, it can say it can detect dark room, lighted room, things like that. So at the sensor level, there are a variety of ways one could kind of go around doing it. Two very common technologies are using a photoresistor, which is basically a resistance whose value changes with the light falling on it, and photodiode, which is a diode where more the light falls on it, the more the current through this thing. So I could use it for a variety of purposes. I can use it to measure intensity of incident light, but you can also use it for differential intensity. That is, I can have two detectors and then kind of look at what is the difference between those. It's often used for detecting color. If you also put a right type of filter in front, for example, you can use it to detect break in continuity. Like I can have the light shining and someone walking past, so kind of a tripwire. I can detect polarization by putting a polarization filter in front of it. I may have very directional light sensors, very broad kind of light sensors. So all those things can be there. And at one level, you can think of a camera also as just a light sensor. It's just that it has a whole bunch of stuff in it. You could certainly use a camera as a light sensor, but it would be very expensive to do so. Okay, so that's a light sensor. The point I want to bring out though is that the purpose, remember here I talked about that the sensors are saying something about one's state or the external world state. Sensors usually do not measure the state directly. Okay, sensors give us some information about the state, but not the state of interest directly. Like for example, let's say I want to know if my home is occupied. That's the state of the home, okay? And because if the home is unoccupied, maybe it should go into the security system should get armed, for example. But there's no sensor which tells me the home is occupied. It will tell me something about that home. Or take another example. I want to detect whether a person is stressed. There's no such thing as a stress sensor. I can measure physiological parameters, and then from that I can draw the conclusion based upon some processing that the state, emotional state or whatever medical state of that person is that he or she is stressed. So this is a very important point, that a sensor measurement is not the state. Measurement is what we get, state is what we are interested in. So sensors, so for example, the sensors cannot say a person is sitting on a chair wearing a particular type of cloth. It might tell a whole bunch of other stuff about it, which is what's the light level, what's the sound level, what's the distance, but nothing directly about the inference. So for us to make sensor measurements useful, I need to process them. And the goal of that processing is to derive the state at a particular point in time that is of interest to us. And same physical quantity can be measured by different sensors, and information about a state can be obtained from a variety of different sensors. So we use multiple sensors because maybe the sensors are telling us something different about the state, and also sensors are noisy, so having multiple of them can compensate for the failures or weaknesses of one or the other. So in this table you kind of see kind of a whole bunch of examples. Some of these are present in our Hexaware, others are not. But the state of interest is one, the physical property, and then the sensing technology. These are kind of different things that one has to be cautious about. So let's take an example. Let's say I want to measure distance to an object. So how far away am I from the wall? Right, that's the state of interest. How far away is a robot from the wall? there are lots of physical properties that can tell that information, and from that I could infer. But they don't tell us the distance directly, but they tell us something about the distance. So like for example, I may bounce an ultrasound signal and it tells us the time of flight, and that tells us something about the distance. Infrared, return signal intensity. So my sensor is measuring, so I'm shining a light, I'm measuring the return signal, and there is some physical relationship that exists between signal intensity and the distance, hopefully monotonic. Two cameras, stereo vision. Single camera, maybe using some assumption about the dimensions of objects. Laser, and a whole bunch of others that you might imagine. Can you think of some other ways you might want to, like you're designing a robot which has to detect distance to the wall? What other ways you can sense it beyond the ones listed here? Thoughts? No, the list is obviously infinite, so I've covered only 0% of it.
Suppose if there are radios in the room and if the robot has a receiver, you can probably measure signals and then estimate distance based on that.
Okay, well, I could use radar, right? Bounce a radio signal, measure radio time of flight. So I could do that. I can measure radio signal strength. What else? Any other thoughts?
Astrometer data with like integrating global position.
With a map, for example, right? If I knew where the robot entered and have a map of the room, so I can do inertial odometry. Okay, so you can imagine kind of a whole bunch of stuff there. Okay, the other one is robot can move with the accelerometer until it bumps into the wall and over stop moving, and then kind of detect that way. Okay, detecting people, right? Use a camera. Computer vision is terrific. But you can also use other kind of things like temperature, movement, color, distance, whole bunch of stuff. So I guess the sort of a takeaway that I want to leave you on with these two slices that there are separate things there. One is what is it about the state that I'm interested in, and then I have some physical signals, and that physical signals tell us something about the state, and it's bridging that gap is what the processing is going to be about. So let's take something which is more a bit more complicated. So let's say we are it's a home where some old people are living, kind of one of those places where you want to make sure that people are safe, or perhaps like one's own home and all. So I want to be able to detect activities, what they are engaged in. Maybe it tells us about health condition. Maybe we just want the home to be kind of a smart home, anticipate the needs and do it. So in a setting like this, first thing is there are broadly two ways you could approach, or a combination of it. I can instrument the environment, or I can instrument the people in the environment, right? So the people part nowadays is we have phones, we wear things like Hexaware type watches, and there are a whole bunch of other things. So there are wearable sensors and there are ambient sensors. So in this case, you might imagine ambient sensors may include things like passive infrared. What does passive infrared do? They are everywhere. They are in this room also.
Senses change in heat.
Yeah.
Does something to do
Where are the PIR sensors in this room? Yeah, the switches, right? Okay, so they are motion sensors. How do they work? Emitted heat, right? Body heat is nothing but IR. We are, if I'm right, I think human body emits around 100 watt. Okay, so that's a good model. in terms of how much heat we contribute to the environment. Okay, so PIR. And there are all sort of PIR sensors. Those are pretty simple, but there are also PIR type imagers in the sense they have a cluster of these things and they can kind of give a thermal map. You can mount them on the ceiling and kind of get a thermal map of it. Magnetic door window, right? Every time door window opens. Now you can imagine each one of these things are telling us something about the actions and the activities that are happening in this space. Temperature, light, humidity. Usually these are often built into the PIR sensor. Vibration, pressure, RFID, camera, microphone, electric meter. I can monitor what's happening in the electric meter and say something about what people might be doing in that home. Water meter, same story. Okay. Tactile things put into the chairs. So you could imagine the space being instrumented, and each one of these sensors in isolation is saying some teeny bit of information. In themselves, they don't tell us the state, but they're telling us something about the state. And likewise, you can imagine a whole bunch of variable things. So there is inertial sensors, the accelerometer, gyro, and magnetometer, which basically tell us acceleration, gyro. What does gyro give us? Angular rate of movement. And magnetometer. Strictly in a mathematical sense, gyroscope doesn't give us any new information. Using accelerometer, you can derive it, but since accelerometer tends to be very noisy, so you also measure gyro directly. Magnetometer tells us the 3-axis magnetic field. Oftentimes, you would see this term 9-DOF IMU. If you go to websites and all, this is M. Inertial measurement unit. There's a company called InvenSense. They dominate the market. They make these chips which has all these three, so 9 degree because each one of them is 3-axis, and they put all sort of processing on it, and output of that you get all sort of cool stuff basically. So very commonly available chips do wonderful things, and you could do indeed things like measure distance traveled and stuff like that, also with appropriate levels of noise. Other variable sensors, physiological, are there is a heart rate. There is also heart rate variability. So heart rate is, if you look at the ECG signal, then you can define the heart rate as peak to peak distance, the inverse of that. Heart rate variability refers to how that peak to peak distance is varying. And it turns out that heart rate variability is indicative of your cardiovascular health, your stress level, stuff like that. In fact, good hearts are whatever. Good cardiovascular health means that your heart can rapidly go up and rapidly come down, okay, kind of thing, okay. And then there is also resting heart rate, and also a whole bunch of stuff which goes in. Breathing rate, that matters. You could use breathing rate to obviously detect what rate you are breathing. What else do you think you can detect from breathing rate? What other state of the human being is breathing rate providing information about?
Sleep.
Sleep, okay.
Exercising.
Exercising. What else?
Whether he's fainted,
Huh?
whether he's fainted or not.
Okay, fainted or not. What else? What about some activities?
It will vary also with the altitude he's at.
Okay, so altitude. Smoking, speaking, right? I mean, those kind of things, right? So it can tell us about a whole bunch of activity, right? Galvanic skin response is the conductivity of the skin. It's basically perspiration. We perspire more when we are under stress. In fact, if you have seen those, the lie detectors, they basically make use of besides heart rate, they also make use of galvanic skin response. So it's indicative of stress. It's indicative of temperature, right? I mean, how humid and all it is. So change in galvanic skin response becomes important. Blood pressure, EMG and EEG are the electrical signals at the skin and from the neurons in the brain. Then there are some of the on-body sensors tell us about the outside, like may have light sensor. Going back to this question about, so accelerometer, IMU on my hand, what all do you think it can tell? What kind of activities you think you can use it for? Almost any activity we do with our hands, smoking, drinking, right? I mean, eating, you could potentially distinguish all of those things as well. So just to show you how our activities manifest in these sensors. So this is data from a book describing work at Washington State. And the sensors are a little primitive because this work is maybe a few years old. So what they did was, in their deployment, they instrumented a whole bunch of apartments where old people were living. And so you see kind of motion sensors, which are the one with M. They have door window sensors, which start with D, and a couple of other sensor types. And then additionally, people were wearing sensors. Though this is pre-Apple Watch, pre-Fitbit era, so they look pretty sort of old-fashioned, but you can get same kind of information now from Hexaware and all. Okay. So what you see out here is this is hand washing activity. So on the top plot, what you see is the motion sensors and certain other, this is an accelerometer, so I guess they had mounted accelerometers on that water taps. So every time someone would open, close the water tap, there would be a signature there. So what you see out here are motion sensors in various places, kind of being triggered, and then this is what is happening on the gyro and accelerometer, and there are 3 traces in each one of them because there are 3 axes, and then there's a pair of accelerometer gyro on the hip and pair on the wrist. So you see this, okay, and it doesn't tell us much, but like just looking from this, I don't think I can say, yeah, it was doing hand washing. But if you look at sweeping, which is another activity, clearly things look different, right? There is something getting captured about the activity in this medley of sensors that we have. And in a sense, the goal that we have is that we want to detect what state or sequence of states the person, the occupants, the space went through from this multi-channel record of sensor data. Okay, and I guess we are out of time. So next on Thursday we are going to pick this trend up.